All right, section 16.2, non-homogeneous equations with undetermined coefficients is our last section for this year. And what we're going to take a look at is kind of extending what we did in 16.1 from a week ago into a more general situation. All right. So to start with, we're going to start with Newton's second law of motion. Do you guys remember Newton's second law of motion? Yeah. Good. We talked about it last time. I know it's been a week. Says force equals mass times acceleration. Right? We did talk about that last week. Yes? It came up. So yes, okay. So we're going to add we're going to start with this, and we're going to add the external force. F of t to the spring force and the dampening force, everything that we had from our forces in section 1. All the forces that we had working with our situation in 16.1. And what that does is that creates a displacement vector, or displacement differential equation, excuse me, that looks something like this. So U of t is, I won't put it equals because that looks a little bit too much like math. This is more of a definition, is the displacement from equilibrium. Then we have the following differential equation. Part of this we saw from last time, and I'll identify that after I've written it out. So this is mass m times u double prime of t equals negative k u of t minus c times u prime of t. And then we have our new force acting upon our equilibrium, which is f of t. So that's sort of mirroring what we did last time. Or if we move things around a little bit from last time as well, we saw that this was m times u double prime of t plus c u prime of t plus k u of t equals f of t, our new force. This is the same equation we had last time, except for what? Do you see it? What's different? Yeah, it's not equal to 0, right? We do not have this equal to 0 now. We have this equal to the new force that we're working with, or that we're acting on our system. Okay, so this is the same as 16.1. I'll say it this way: when the force equals 0. Now I feel like I'm talking about Star Wars or something like that. This is the same as when f of t equals 0. All right, all of what we're doing right here has a name. We call an equation such as the above. We call an equation like this. We'll say it that way. Homogeneous. When f of t is 0, and non-homogeneous, I know that's very creative, but non-homogeneous when f of t is not 0. And our goal is to find a solution to such an equation. Okay? In some cases, we find general solutions. We did that last section. Sometimes we find specific solutions. In particular, solution has this kind of a form. So if we have a particular solution, u sub p of t, then if u of t is any other solution, then m of u minus u sub p double prime plus c of u minus u sub p double prime, not double, single, plus k of u minus u of p. This is equivalent to having m of u double prime plus c of u prime plus k of u minus each of those with u sub p, so m u p double prime minus c u double single prime. That sounds funny. Minus k of u. This would equal f of t, because the first one's a solution, right? Let me put this in here, right here. This is f of t. This is also f of t, right? So this would be minus f of t, which would be a grand total of 0. So what does that mean? Well, it means that u minus up is actually a solution to the homogeneous equation. So if u and u sub p are solutions to the non-homogeneous equation, then the subtraction of them, their difference, is a solution to the homogeneous equation. I'm going to write that over here because I've run out of space. So that is u minus u sub p is a solution to the, we'll call it corresponding homogeneous equation. You bet.
Are those u's supposed to be u sub p's?
Yes, they are. Thank you for noticing my slip up. I left a couple of them off, didn't I? Thanks, Caleb. Is that good, Tally? All right. So this leads us into theorem 2.1. I'll write it in here since I have space. And theorem 2.1 says the following. This is the culmination of all of the details we just outlined. Let u equal c1 u1 plus c2 u2 be the general solution of m sub u double prime plus c u prime plus ku equals 0. And let u sub p be any solution of m u double prime plus c u prime plus ku equals f of t. Then the general solution of mu double prime plus cu prime plus ku equals f of t is given by u equals c1 u1 plus c2 u2 plus up. Basically, the nuts and bolts of what we're going to do is we're going to do what we did last time in 16.1 to find this piece right here, the c1 u1 plus c2 u2. And we're going to have a particular solution that we add to that. And we're going to start with something that feels a little bit like we're getting something for free. So you'll see what I mean. All right, so let's take a look at the first example. The directions say the following. Find the general solution of the equation given a particular solution UP. All right, so our differential equation is u double prime plus 2u prime plus 5u equals 15e to the negative 2t, and u sub p that's given to us is 3e to the negative 2t. Does anybody else feel like what we're about to do is sort of cheating? Why does it feel like it's cheating, Caleb, for those who didn't catch it yet? They gave us u sub p, didn't they? So they're starting out where this doesn't really look and feel a lot like last time. We've just got this extra piece of information given to us, and at the very end, we're going to add that to what we already did from the last section. Okay, so we're sort of easing our way into this. Do you remember what we did to find where this is equal to 0? Because that's where we're going to start. What did we do last time to do that? We used a characteristic equation, r squared. Go ahead.
Plus 2.
Good. Plus 5 equals 0. So we created the characteristic quadratic equation, and we solved it, right? And if we could factor it, that was great. And if we couldn't, then we had other methods for dealing with it. This one doesn't factor. So you guys had the fun time of remembering the quadratic formula. Some of you have had it more recently than others because you've helped maybe people with it. So what does it look like for this?
-2 plus or minus root 4 minus 4 plus 5.
So this is 1 plus or minus 4i over 2, and then, I'm sorry, not 1, 2. And then, like you said, James, we have 1 plus or minus 2i.
Negative.
What did I miss?
It would be -1.
Oh, you're correct. Thank you. Get that in there. Okay? Everything else okay? What did we do after this? And that looks like algebra. We found our general solution, right, with the C1s and the C2s, and it was based on whether or not the answer was real or complex, and this one, of course, is complex. It had the form that looked something like this. We had C1 e to the...
U.
Right, and the u came from here, right?
T.
So this would be negative t, and then cosine of v, which was from here. And so that would be then 2t. Excellent. And then what?
Plus C2 e to the negative 2 sine.
All right, good. That's what we did last time. So this is for the homogeneous equation. I keep wanting to put an E on the end. There's not. That's better. For the homogeneous equation. So for our solution, or our final solution, or our final general solution, I don't care. You're just going to have to identify that this is not the same U of t. Their notation that the book is using does not differentiate between their notation on this. So it's going to have that form that we already had from before. So all of that's going to stay the same. So C1 e to the negative t cosine 2t plus C2 e to the negative t sine 2t. And then according to theorem 2.1, what am I going to do next? We don't even have to plug in the 0. We're just going to add that to what, Taylor? What do you have, Tally? Yeah, u of p that they give us. Yeah, the u of p that they give us is actually what goes on the end here. That's it. So 3e to the negative 2t. Okay, so does this feel like we did anything different than last time? No, it really doesn't. But we're not always going to be given u sub p, right? There are going to be 2 or 3 of them, I think, that I gave you homework. I think it's just 2. Where they give you u sub p, and this is all you do. You just add the u sub p onto the end of what you would have already done from last time. Okay, so what happens then if you are not given u sub p? That's where we're headed next. So let me write a couple of details about this since I've said it out loud. So, nice. This isn't even in my notes this way. This is nice if u sub p is given. But it isn't always, right? So then what? Well, if the f of t equation isn't too complicated, then we can make an educated guess. And find u sub p. So that's where we're headed next. We're going to be looking at some things that are not too complicated for f of t, make an educated guess. Now before I do that, I'm going to go back to the u sub p they gave you for the last problem and see if you can notice anything that might be helpful for making an educated guess when your equation for f of t actually looks something like 15e to the negative 2t. What might be an educated guess for how u of p might look? Just to compare quickly. I mean, it looks like maybe, but it may not even be that. But try to think just more generally. What are some features that they do have in common first? Yeah, they've got the same e. I mean, they both have e in them, right? The exponent for e is the same, right? And the coefficients don't necessarily have to match. So the question of what the coefficient actually is might be sort of up for discussion at that point. But they definitely have the feature that the part that is the same as this exponential part of it, right? I'm going to do a different example than that one right now, but I did want to draw your attention to that. So let's take a look at the second example here. Whoops, hang on. So we're going to find the general solution of the equation. And the one that we're going to work with here is u double prime plus 2u prime plus u equals 25 sine of t. The left-hand side is actually something we did last time, which is why I picked it this time. So let's start out with the left-hand side. We'll deal with the right-hand side, u sub p stuff, in a minute. So for the homogeneous equation, what's going to happen? Okay, say again for me, James Ladler. Right. So r is just -1. So what do the solutions look like? What does u of t look like in that case? Do you remember? That one's a little different than the last one, right? Mm-hmm. So like this, e to the negative t? Okay, and then what? Right, it's got a factor of t in it, and then it's the rest the same. Okay, does that look familiar? All right with that? So now the right-hand side. So my right-hand side is 25 sine of t. So what do you think that we might need, roughly, for the right-hand side's u sub p to look like? something with a sine t in it seems reasonable. The problem is that as we take derivatives and antiderivatives, of course, of sine, what happens as we take these derivatives and antiderivatives? We get different signs. What else do we get? What happens with sine? We sometimes get cosines involved, right? So our general form is actually going to have sine of t in it. And notice the angle's actually matching. So this is t. This is also going to be t. If it were 2t, it'd be 2t, and so forth. We'll see that happen here in a minute. But we're also going to say that the general form could have b cosine t in it. Okay, so our general form is going to have sine or cosine, coefficients of a and b. The angle for, in this case it was t, is going to match. What we're going to do is we're going to actually find our use of p. In this case, we're not always going to find that. In some of the cases, we're going to just leave it as this sort of a form and be done. But we can find this one relatively easily. So we're going to take some derivatives here, and we're going to plug them into the general equation that we started with up here, u double prime plus 2u prime, and so forth, and figure out what u of p is, because this is a very simple equation compared to some of the other ones you could deal with. So the first thing we need to find is we need to find u prime, and then we'll find u double prime. So somebody tell me what u prime would be here. James mentioned getting some negatives and positives out of this. A cosine of t. Good. Minus b sine of t. And how about the second derivative?
Minus a sine of t minus b cosine.
Everybody good with that? Okay. We're going to use these three solutions now, u prime, and u double prime, into our original equation in their proper locations and solve for a and b. Okay? I'm about to run out of space on this slide, so I'm just going to switch right now so that I don't have to copy paste in a moment here. You know you have, just as a reminder, u double prime plus 2u prime plus u equals 25 sine of t. So we're going to do u double prime. Well, that's the same one that we had kind of started with negatives everywhere, right? So we have negative a sine t minus b cosine t plus 2 times a cosine t minus b sine t plus the original one that we were using as our general form, which was a sine t plus b cosine t. And this is all supposed to equal, when we're done, 25 sine t. Everybody good so far? Cleaning up, collecting like terms, all that good stuff. So that's where we're headed next. So we have negative a sine t minus b cosine t plus 2a cosine t minus 2b sine t plus a sine t plus b cosine t equals 25 sine t. All right, collect me some signs on the left. There's sine t, sine t, sine t. How much sine t do I have? What's going on here? Oh goodness, those canceled, didn't they? That's friendly. Good, so negative 2b sine t. Now what? How about the cosines? Those canceled as well, didn't they? 2a cosine t. They don't always clean up quite so nicely. Sometimes there's more of a mess involved in doing the identification. What we're about to do next is going to feel kind of like what you did when you did partial fractions. Basically what we want is we want this piece, because it has sine t in it, to equal this, right? So what does that mean? It does mean that a is 0. So let me get to the a is 0 in a minute. Let's look at the b value. If these two are equal, then it has to mean that negative 2b is equal to 25, correct? And we're just identifying piece by piece. And it means this would have to equal the part in it over here that has cosine in it. Well, there isn't. So technically you could say that this is 0 cosine of t, correct? Which would mean that the 2a also has to equal 0. Now, in most cases, you will end up with not just one variable equaling the constants here. You're going to end up with a system of equations, right? You might end up with something like a plus b equals 1 and a minus 2b equals -5 or something like that. So you have a system of equations, two variables, two equations. You should be able to solve for them. In doing so, on this one, we find out that b is equal to what? Yeah, and it's negative, right? So negative 25 halves. And of course, a is equal to 0, which means what is my particular solution now that I have found have found a and b? What is u sub p going to be on this particular one? I think it's cosine. Isn't it, James? Okay, because that's the b value. Yeah, so cosine of t. And then I don't have a value, so I don't have a sine t, right? So this is actually the one that would work for my particular solution, which maybe have been a little counterintuitive to what you thought. You probably thought it was going to be something with sine in it, and then it's actually cosine only. And of course, it could be a combination of the two, if the a and the b had neither one been equal to 0. So what is my general solution? Well, what's it look like? C1, what's next? E to the negative t. Can you keep going for me, Nathan? Good. And this is still a general solution, right? It's not a particular solution. Why?
We have C1.
Yeah, we still have C1 and C2 in it. But it is a little bit more specific than had we just put it in with the A and the B involved, right? It was fairly straightforward to solve for A and B. If we were given some initial conditions, could we find C1 and C2? Yeah, we definitely could. There's no reason we couldn't handle doing that. The information given in this one doesn't allow us to do that. We don't have enough given to us. But any questions on this one? Okay, so what I'm going to do next, and I probably should have just taken a picture of it. Does anybody have their textbook with them? Okay, I'm going to do that then. All right, this table, it's in your book. What page is it on, just so that everybody knows? 1084. 1084, helpful table. It's a table that I'll give you on, I know I'm writing in the book, aren't I? This table I'll give you when you do your test. This one tells you if you have these f of t equations, then this is the initial guess that you would be using. So you can see we've already talked about the first one, that was e to the r sub 1t, and this is a e to the r sub 1t. Okay, so this one tells you how you would modify the guess if there's not an r1 and an r2. So the case is there's not an r1 and an r2 if it's a duplicate root, right? If r1 is equal to r2, so to speak, or whatever, there's only one root of the solution, or one root of the equation. If you have a cosine or a sine, you have a cosine kt, b cosine or sine kt. And I already mentioned the fact that kt is the angle, it stays the same, so you do need the same angle involved for this to work. This didn't come through very clearly, but this is a polynomial, r to the n. And so you have coefficients that are each of a different c sub 1 value. So if it was a polynomial that was a trinomial like t cubed or something like that, or degree 3 is what I meant to say, then you would have t cubed, t squared, t to the first, and so forth down the line. And this is, you modify it this way. All right, so these pieces are if you have a e involved with the sine and the cosine, of course, and then we've got the other one on the bottom. So this is telling you how you make your initial guess. So I wanted to bring your attention to that. We're going to do an additional one with the same directions, it looks like, using that table. So keep that table handy. I'll flip back to it if we need it. And here's our third example. So we're going to determine the form. So slightly different directions. We're going to determine the form of the particular solution. So we're sort of going to practice using the table, but you'll see why this sounds a little funny. So here's u double prime plus 2u prime plus 10u equals 2e to the negative t plus 3e to the negative t cosine 3t plus 2 sine 3t. The right-hand side of this is not simple. The last one was, right? It was 25 sine t. Really, I know. Surprise. There's a lot going on. It can be broken up into pieces, however, and matched with what that table was telling us to do, and that's what we're going to look at. So to start with, for the homogeneous equation, let's figure out what we would have for r. Because we may need to modify suggestions based on if we have 1 or 2, if they're real or they're complex and so forth. So somebody tell me what we're going to get for r equals. I'll start you out. -2, now what?
Square root of -36.
Okay, so you got -36 over 2. What's this going to end up looking like? It's -1 plus or minus 3i. Excellent. So those are our r values, u and v and so forth, and what we were looking at before. And what would u of t look like based on this? So like the first one we did, right?
C1.
Mm-hmm.
U
Right?
-2. Cosine of 3t.
Excellent.
So some t. U -t. Sine of 3t.
All right, so let's talk about what our initial guess would look like, and then we'll talk about how things change because of this. So our initial guess and this is for u of p. Needs to come from what's on the right-hand side, right? It's based on what's on the right-hand side. All right, so using what's on the right-hand side, the first thing we have is we have 2e to the negative t. So using that information, what would our u sub p look like, the general form of it, using that table or what you know already? What would it have? Yeah, and with some coefficient, maybe a. So a e to the negative, was it 2? T, just negative t. Okay, how about this next piece? Oh, I should have done it piece by piece, sorry. What do you have, Taylor? It would be, but I've already used A, so I'm going to go with B.
Oh.
Uh-huh. Tally, keep going. Mm-hmm. Good. And you're getting that from the table, right, Tally?
Yeah.
You're matching that piece up. Good. And we have one more piece here at the end that looks distinctly different than the one that I just did, right? Because it doesn't have an e to the negative t in it. So what would that piece do for us? D sine of t, 3t, right? Sorry. And then what's next?
Plus e cosine.
Okay, is everybody good with that so far? Okay. Here's what happens next. Well, I'll distribute that e to the negative t, and you can as well. But aside from that, what we're going to do is we're going to compare this to the general solution we have already, the u of t equation that we already created. Oops. That's what happens when you start talking and not writing. Okay. b e to the negative t cosine 3t plus c e to the negative t sine 3t plus d sine 3t and e cosine 3t. Parts of this look like what we already have in u of t. Somebody identify something that looks the same. Right here and right here. Anything else? I think that's it, isn't it? Okay, those two pieces already match what I have in u of t. I don't need to include them then. Why? Why can I just leave them out? Because it would just change the constant, right? This is something akin to when you do just antiderivatives the very first time you learn them. If you were to do an antiderivative of 3x plus 2, it would actually be the same as if you did the antiderivative of 3x plus the antiderivative of 2. And you did, oh, this is 3x plus c, and this is 2. I'm sorry, that's not 3x at all plus c. 3 halves x squared plus c, and this is 2x plus c, and this is a c1 and this is a c2, and we say, well, that's sort of silly. If I just combine the c1 and the c2, it's just some other constant, right? So I can do them all at the same time and just put the constant at the very end. So in a very much the same way, we can do that here too. So I don't need these additional pieces of my solution because the coefficient at the beginning, b and c respectively, will get absorbed into the changed coefficient of the c1 and the c2 that are used. Okay, everybody good with that? So I don't need those parts of it. Or likewise, you could say that you don't need the c1 and the c2. I don't care which one you say you don't need, so you can make your pick. Okay. So our u equation. Let me say it this way, removing duplicates, we have u of t equal, I'll write it the way we did before, c1 e to the negative t cosine 3t plus c2 e to the negative t sine 3t plus a e to the negative t plus d sine 3t plus e cosine 3t. And like I said, if you don't want to use the E1, the C1 and the C2 here, and you actually used B and C here, it'd be the same thing. I don't care what you call it or which piece of it you continue to look at. So as you're looking at solutions, just keep that in mind, like in the back of the book or in the problems that they do. Remember, the directions actually just said to determine the form. So we're not actually finding A, B, C, D, E, or A, C1, C2, D, E in this problem. We're just finding the form, and this is the form that we're looking for. All right, let's take a look at another example. This one requires a little bit of writing. Number 4, a mass of 0.1 kilograms stretches a spring by 2 millimeters. The dampening constant is C equals 0.2. External vibrations create a force of f of t equals 0.1 cosine 4t newtons. setting the spring in motion from its equilibrium position with 0 initial velocity. Find an equation we'll say find a general equation for the position of the spring at time t. All right, so we are given C. C is equal to 0.2. The first thing we're going to actually do is we're going to find K. Let me write this at the top again. This is M times, or we'll just put U double prime of T. Well, let me do this. C prime plus KU plus F of T. Just put F, abbreviate. First we find K. So force, or force, which is mass times acceleration, equals the K value, which is what we're looking for, times displacement. We'll call it X. So the mass is what for our object? I think it told us, right? 0.1, yeah? Acceleration, 9.8. This is gravity, right, for our spring. Okay, so what we're looking for, what is the displacement? Yeah, so it's the 2 millimeters, so it's 0.002 meters. So somebody solve for me really quickly. What do you get for K? 490 is correct. All right, so let's set up our initial differential equation. So our differential equation is, the mass that we decided already was 0.01, or 0.1, excuse me, 0.1 U double prime. And then what? C is 0.2, it's given to us, so 0.2 U prime. We just found K is 490 U. Equals, did I write that in? Oh yeah, there it is. The force, which is 0.1 cosine 4t. Okay, is everybody good with that? I'm going to copy this to our next screen. All right, we're looking for some solutions to this now, right? That's what we're actually supposed to be finding. So let's start out with our homogeneous equation. r equals, well, it might actually be helpful to see a little bit on this one. Got some weird decimals involved. I'm not even sure I really want to deal with the decimals quite like they are. Could we get rid of the decimals?
That's foolish talk.
That's foolish talk. What can we do to get rid of the decimals? I don't want decimals involved in a radical. I mean, that's just not helpful at all.
Multiply by 10.
Multiply by 10. Yes, this is r squared plus 2r plus 4,900. All right, so let's find out what r equals. And for the moment, at least, your book is keeping all of this exact, so let's not use some decimal approximation. Let's actually find the actual value with the square root ugliness involved. So I've got -2. Apparently every problem we're going to do today has a -2 in front. I don't know why that's happened, but plus or minus what? 4 minus 4 times 4,900. Yeah? Because that looks like a good number. Divide by 2. All right, what is 4 minus 4 times 4,900?
Negative 19,596.
Negative 19,000 what, Caleb? 596. Okay. Simplifying radicals. Man, it's been a long time since you did that, right? Yeah. Does 4 divide it? I'd at least like 4 to divide it because then I can drag out a 2 and cancel it with the 2 in the denominator. I think so.
Square root of 4,899.
This is -1 plus or minus I square root what?
4,899.
All right, so then I at least don't have a denominator of 2 anymore. So I have a recognizable u and v for my particular solution, for my general solution to the homogeneous equation, right? All right, so let's find that then. What would u of t be with this funny radical involved? C1. Yes. Now what? Good. It is cosine first. Uh-huh.
Square root of 4,899.
Times t, right? Okay, so just for fun, I'm going to put the t first so that I don't worry about it being unintentionally grouped underneath my radical. So this is cosine of t square root 4,899 plus c2 of e to the negative, or times e to the negative t. Sine of the same silliness. All right. I didn't use the word nonsense. I did use the word silliness, right? Okay. All right, we need a u of p next, right?
Yep.
Yes. We need to find u of p. You know what the general form of u of p is. What would it be? Now, careful. You remember u of p comes from the right-hand side. And this is actually a fairly simple one, right?
A cosine 4t plus
A cosine 4t plus
b sine 4t.
b sine 4t. We're going to find the a and the b. And I think that's where we'll stop on this problem. Can we find C1 and C2? Yeah. It's going to be messy because we got those radicals involved. But finding the a and the b doesn't involve radicals whatsoever, right? How do we find a and b in this particular problem now? Well, it's not partial fractions, but it feels like it, right? What do I need to do? So we found that u of p equals a cosine. What was my value? 4t, thank you. Plus b sine 4t. What do I do next, based on the last works that I did? This, right?
Yeah.
Derivatives. What's the derivative of the first one? This is more complicated for some reason here. Let me find out real quickly why.
4a.
Negative 4a cosine 4t plus.
Sine 4t.
Oh, I'm sorry. Did I write it wrong? I sure did.
Forgot your derivative.
I did.
Okay.
I don't know. All right, negative 4a sine 4t plus 4b cosine 4t. I need to do this again. U sub p double prime. Now what? Yes. So the first issue is that this is a little more complicated because we have a angle that's 4t, right? It's going to change the coefficients every time. We didn't have that changing last time. The other reason it's a little more complicated is because our original equation has decimals in it, doesn't it? I suppose we could get rid of the decimals by multiplying everything by 10. Would you like to do that? That'd make it a little bit easier. So my original equation had, without the decimals, would be u double prime plus 2u prime plus 4,900 u equals cosine 4t. And then we'll put our second derivative, first derivative, and original into this equation to solve for a and b. So our second derivative, the last one we just took, was negative 16a cosine. What's that? No, because if it's a solution of the original one, it will be a solution of the original one times 10. So we wouldn't need to. Yeah, we wouldn't need to. Negative 16 cosine 4t minus 16 sine b, right? B sine 4t. I need this one plus 2 times the next one. Can I multiply by 2 as I go? Are you guys good with that? So good with that. Okay, so this would be minus 8a sine 4t plus 8b cosine 4t. And then the last one needs to be 490 times this one. But none of them have coefficients already, so we just have 490a and 490b. Not 490, 4,900, sorry. Cosine a plus 4,900b. There's an a in there. Yes, I got my variable in the right spot. Thank you. And then b cosine sine 4t, and all of this is supposed to equal cosine of 4t. Holy moly, let's collect our cosines. There's a cosine, and there's a cosine. How many cosines do I have? Negative 16, positive 8, and 4,900. So 4,900 minus 8. Go.
4,892.
And that would equal, yeah, I should have had a, oh wait, hang on a second. Were they all A's? They weren't all A's. I can't combine them. Oh, shoot. Oh, man.
No.
I can combine a couple of them, right? All right, 4,900A and negative 16A is what? 4,884A minus, was it minus? No, plus 8B equals 1. Is that right? The one from right here. So these coefficients all have to add up to 1. Is everybody good with that one? Yes. And then the other coefficients, the ones on the signs, they have to add up to what? 0, because there is no sign on the other side. So some of them combine. Which one? The B's combine. I have 4,900B minus 16B. That sounds like a number I've already dealt with. 4,884. B minus 8A equals 0. System of equations. How do you solve systems of equations? You have options. Elimination would be an option. Yep.
Small matrix.
Substitution would be another. A matrix would be one. You could actually use a grapher if you wanted to. You may have technology that will allow you to deal with this as well. I didn't write down the solution for this for A or B, so you guys get to try and find it.
Integration by parts.
I don't think integration by parts is a viable solution at this point. Is 4,884 divisible by 8? I don't think it is, actually. Evenly. No, it doesn't. But it's not awful, right? So just for fun, let's solve the second one for A. So 4,884B equals 8A. What does happen? You kind of nodded your head for me, Jordan, like you tried to solve it or divide it by 8. What did you divide that by 8? What do you get? 0.5? It doesn't, is it even?
Oh, over 2.
Over 2. Sorry, I didn't hear you right. Okay, over 2B. So we can actually, if you want to do substitution, you can plug that into the other equation for A. So you have 4,884 times 1,221 over 2. B plus 8B equals 1. It turns into a whole number, right? Yeah.
Very, very fun one.
Is it a very fun one? What do you get when you combine the whole number that this turns into plus 8? I don't have the right answers.
981,682.
We can't add
We don't have an A anymore. Yeah. 2,981,000 what?
682, and you're adding the 8 to it. 690.
I think that gives us a value for B. It's an amazing value, isn't it? Almost 0. That's exactly right. 1 over 2,981,690.
You might just say 0.
No, but we can say almost 0. How would we find A?
plug me in.
Yeah, we'd plug that in for B. Or plug B in for it. So 1221 over 2 times 1 over 2,981,690. In fractional form, because you guys are math people, so you like fractions better than decimals, right?
I'm a physics major. I don't know what you're talking about.
Physics people, I think, probably like fractions better than decimals, too. I'm just guessing. Do you? No? You guys like decimals better? Oh, bummer. All right, well, pretend you're a math person for the moment and find me the fraction that goes with this. Your calculator likes fractions just fine. Did you get one tally? It won't do it.
It's 1221 over 5963383.
They're telling us.
1221. It won't simplify. Is that what you're saying? Okay, over what was the number? 5 million?
963,380.
Awesome. What beautiful numbers. Let's write our solution and be done. Man, that was work. Okay, hang on just a second. Let's write our solution. You're not done yet. You're out of paper.
No, we're almost. This is the last example, right?
This is our last example. Yes, it is our last example. Okay, let's write our solution out. Where did it go? U of t equals C1 e to the negative t cosine t square root 4,899 plus C2 e to the negative t sine t square root 4,899 plus A. What was A? That was the one that had the 5 million, right?
1221 over 5963380.
5 million. Slow down for me again, Caleb. One more time.
5963380.
We're smart.
Was this one sine or cosine? Sine first?
Cosine.
Cosine first? All right, and then plus 1 over 2 million.
Isn't it 14?
It was 4t, thank you. $2,981,690. Sine 4t. Is that right?
That is correct.
A times cosine, B times sine, since that's the order we gave it in, like this. Let me put a note in here. Your book makes mention of the fact that using the info given, we can find C1 and C2. So we're not going to find them. Okay, we're not going to find them, but let me just talk through with you what you do know about these. How could you find C1 and C2? Well, you're given some initial conditions because this had context, right? It was a spring. What did it tell you some of the initial conditions are?
Zero initial velocity.
Ah, the initial velocity was 0. That was a condition. I think it gave you something else too. The initial position, right? Huh? Yeah. The initial position was 0.02, right? Was it 2 millimeters?
Yeah, 2
So 0.002 meters. So we can use this to find C1 and C2. Okay? It's not undoable at this point, but at this point you're looking at your technology simplifying the pieces of information because it's kind of messy because we've got exponentials, we've got radicals involved, and we're just going to have to, like fall down and decide that decimals are probably going to be okay, even if we don't like them. So that's where you would head after this point. So I'm not going to go through those pieces, but that's what you would do. All right, I need to give you a list of homework problems, right? Yes, by all means. Okay. By no means, yes, by all means. All right. This is page 1088. 2, 3, 5, 8, 12, 13, 15, 18, 20, and 21. Oh. Okay, but like two or four or something of them at the beginning are the ones where they give you U of P. Some of them are ones where you're just identifying. Some of these pieces are not messy. The end thing that we're doing is messy. 2021, have fun.
Okay, if that was 6 of the 10, that would be